Whenever you have a flat surface underwater, let me sketch it for you to make it a little bit easier to understand. So this is the surface of water, and you have a flat surface submerged in water. If I ask you to sketch pressure distribution, you would tell me that over here, pressure is smaller than over here. So you sketch your pressure distribution over here. And let me remind you that the length of each arrow represents the magnitude of pressure at that point, right? So at the bottom of the plate, pressure is higher. On top of the plate, pressure is lower, right? So here, whenever your plate is flat, the only thing that changes is the magnitude of pressure, the length of the arrow. The direction of the arrow is the same for all of those points, right? Now, if we have a submerged curved plate underwater, something like this. This is a submerged curved plate. In addition to the magnitude of pressure, the direction of pressure will change too. Why is that? Because pressure arrows should be perpendicular to the surface, to the plate. So if this is the pressure over here, then a little bit below that it should be perpendicular. So it would be something like this. Over here, it would be something like this. Over here, something like this. So in addition to the magnitude of pressure, the direction of pressure will change as well. In order to make our job easier to calculate the resultant force on curved surfaces, we are going to calculate different components of the resultant force. And by components, I mean the horizontal and vertical components of the resultant force. Okay, so this figure over here should be very familiar for you because we used it to derive the equation for flat surfaces, right? We're going to use it. We're going to assume that this plate is curved. And we are going to use this analogy to derive the equation for horizontal component of the resultant force. All right. To do that, we need to consider a very, very small patch with the area of dA, right? So I'm going to actually, this is the small patch with the area of dA. I'm going to exaggerate its size and draw it over here. So this is the small patch dA. So the area of that would be dA, and the force on top of it, the resultant force, would be, I'm gonna perpendicular to it, and it would be dFr, right? All right, we can actually write down the components, different components of this resultant force, vertical and horizontal components. So this would be the horizontal component. I'm going to call it dFH, and there is going to be a vertical component like this, would be dFV. In this slide, we are going to talk about dFH, the horizontal component. All right, I'm going to write down the equation for force, or the amount of force that is exerted on top of the patch dA as a result of the pressure distribution. So dF is equal to pressure at that point times dA. Now, if I want to calculate the dFH, and this is the Fr, the resultant force, it would be pressure at that point times, all right. Now, because this is going to be the horizontal force, I need to find out the basically projected area onto the vertical plane. What do I mean by that? So if this is my vertical plane, imaginary vertical plane that I'm considering, right? What would be the projected area of patch dA on this imaginary vertical plane? It would be this line, right? It would be projected like this. And what would be the area of this projected one? It would be dA sine of theta. How do I know that? Because remember that this angle is theta. So this angle would be theta as well. Perfect. Now, so instead of dA, I can write dA sine of theta. And to make it actually super clear for you, I'm going to define this dA sine theta as projected area onto the vertical plane. So this is the horizontal force only on top of the patch that we have selected, the teeny tiny patch. Now, if I want to calculate the total horizontal force, I need to get an integration of the entire thing, right? So over the area, I'm going to take an integration of the entire equation, and it can be written as this. So simplifying this, it would be FH is equal to P times AVP. And again, AVP over here is vertical projection of the plate. Let's substitute pressure in this equation, and horizontal force will be equal to gamma of the liquid, H bar, and AVP. Note that H bar here is depth to the centroid of the vertical projection of the curved plate. And eventually, YP would be equal to Y bar plus I bar divided by Y bar times AVP. So notice that all the equations that you learned are the same thing. The only thing that you need to pay close attention to is to use the area of vertical projection, okay? Which in our patch case, the area was dA sine of theta. Depending on the geometry of the curved surface, this area might be different, okay? And this would be clear when we are going over some examples. I have summarized some information from the previous slide, and in this slide, I'm going to show you how to derive the vertical component, or F sub V, of resultant force F sub R. All right, take a look at the free body diagram over there. Right now, using the orange pen, I have drawn horizontal projected plane, right? So what I'm going to do, as I said, I'm going to find the differential force, the vertical differential force on the patch, on the teeny tiny patch that we have. So to do that, I need to have pressure times area, the horizontal projected area of that small patch. That horizontal projected area would be the area of this surface that I'm going over with the green pen. So I'm going to write down, this is horizontal projected area, which can be written as dA, differential area, times cosine of theta. I'm going to plug in this into the equation of force, dA cosine of theta. Now, you probably still remember that whenever we have a horizontal plane, pressure is going to be constant and it's not going to change. Why is that? It's very simple. So this is if this is the water surface And if I have a horizontal plate over here, the pressure at any given point on this horizontal plate is going to be the same. Why is that? Because pressure is directly related to h, or depth of these points. And because all of these points have the same depth, pressure is going to be equal to gamma times h for all of the points on the horizontal plane, right? So I'm going to simply replace that over here. So it would be gamma h times dA cosine of theta. Perfect. Remember that dA cosine of theta is the area of horizontal projected surface, and h is the depth of water above that area. So if I want to show you where h is, it would be somewhere over here. It would be this. This is, there we go. I'm showing you the horizontal projected area, and this depth would be h. Okay, so also we know that this horizontal projected area is dA cosine of theta, right? So now, if I tell you that you have dA cosine of theta and you have h in this equation over here, the multiplication of h times dA cosine of theta gives you the volume of the column of water right above your patch, right? So simply, I can write this equation as gamma times dV, which is the differential volume right above your patch, your teeny tiny patch, right? Great. Now I just need to integrate this equation. So I'm going to integrate this equation over the area of the curved surface submerged underwater. It would be dFV equals integration over A gamma times dV. Perfect. Now based on this, my FV, or vertical component of the resultant force, would be equal to gamma times volume. So this volume is the volume of the water right on top of your submerged plate. I'm going to define it over here. From chapter 2, you should still remember that gamma, or specific weight, was W, or weight divided by volume, right? So volume can be written as W divided by gamma. Now if I take this equation and put it in force equation, vertical force would be equal to W. It means that vertical force is equal to weight. In other words, it would be the resultant vertical force component acting on the plate is equivalent to the weight of the volume of the liquid, in our case water, above the plate. So I'm going to write this definition over here for your reference. So we found the magnitude of vertical component of the resultant force. The last thing that we want to find out is the location that this FV acts on the plate. The force, or FV, acts through the centroid, or C sub V, of the volume. So location of this, it acts through the centroid of the volume. Now that we found horizontal and vertical components of force, the magnitude of the resultant force can be easily calculated, and also its direction. And we're going to talk about this in next slide. This slide does a great job recapping what I've been talking about. Whenever you are faced with solving a problem involving a curved surface submerged underwater, you need to calculate horizontal and vertical forces of the resultant force. And you can see that here, the resultant force, this is the line of action, and you can see the resultant force acts on center of pressure. This is the center of pressure. To calculate horizontal force, you need to figure out the vertical projected plane. This is the vertical projected plane that I am going over, and calculate horizontal force. And then similarly, to calculate vertical force, this one over here, you need to calculate, or you need to find out the horizontal projected area and find out FV. Once you have these two, calculating FR is pretty easy, and it can be calculated as FH to the power 2 plus FV to the power 2. And this would be your resultant force. Also, in this slide, you can see the summary of what FH and FV are. FV is the weight of the volume of the liquid above the plate, and FH is the resultant pressure loading on the vertical projected area.